So everyone has been asking. Homework will be assigned this week, today or tomorrow, I'm anticipating. And I'll make sure to give a fair amount of time. I'm not gonna. So the deadlines that are listed on Canvas, I think I've got the exam dates correct. Those are on the syllabus. So those are ones that are important to plan around. The homeworks are going to be a little bit more dependent on my travel, the pace in the class, and so on and so forth. But I'll make sure that you'll always have enough time to work on the homework and ask questions. I'm not too concerned about it. So a couple of notes on the homework itself. I really, really hate busy work. And I notice that a lot of textbook problems, they make them arbitrarily complicated, like these contrived scenarios that you're really never going to encounter in real life. So I don't much prefer those. I like to write my own problems. But that also means that writing your own problems takes a lot of time. So I tend to reuse stuff from previous years, or I'll change the numbers a little bit. In my mind, the homework is sort of like showing up to lecture. I make it worth, I think, 10 to 15% of the grade. So it's enough that you guys care to do it, but not so much that the grades depend on it. My means of assessment are always going to be the exams. So if you want to be a little dishonest and not do the homework as much and rely on your friends, it'll come back to haunt you. That's sort of how my philosophy is. But I do change the problems to make sure that it's fresh, but just keep it in mind that doing well on the homework is not an indication that you're going to understand and do well on the exam. And I'm okay with that policy too, because at the graduate level, everyone's here to get their PhD. And the way that you should be thinking about these classes, I mean, don't worry about the grades too much. I mean, you have to get the grades good enough to pass the qualifying exam and advance through the program. But at the end of the day, your success as a graduate student is not going to be dependent on your GPA. So really, the homework is there as problems that I think are important, concepts to understand, and I write problems to test concepts and to teach you something. So there's always going to be some sort of a journey that you're working through to some extent for the homework problems. Some of them are just mechanical. Can you do an energy balance? Can you do an entropy balance? Can you put the systems together, come up with an answer for the efficiency? But a lot of the other ones, I'm really writing them to test concepts. And so I just want everyone to approach the homework problems with that perspective in mind. And I will tell you that when I applied for this job, I did not have my GPA for graduate school on my resume. Nobody asked about it. Never came up. How well I did in classes didn't matter, right? What's important when you're applying for a job at the graduate level is, are you passionate about your work? Do you understand what you're talking about? Can you communicate complex research ideas effectively? And no one's going to say, oh, well, I see you got an A- in thermo. I don't think you're the right material for Exxon, you know what I mean? So that's not the case. But that being said, this is the last opportunity, basically, in most everyone's lives, the last opportunity to have someone stand up in here and basically say, these are what I think the important concepts of topic X, Y, and Z are. That's a luxury. It's very, very nice, because it makes learning so much more efficient. So as you say, so this is my impassioned plea to sort of treat the homework with respect and use it as an opportunity to learn. Because in the future, when you're trying to transition to understand a new topic, it doesn't take a semester, it takes years. Because you've got so much stuff going on. And so as a faculty member, when we're trying to go from studying one material to a different, or trying to retransition, right, you have to take an entire sabbatical. So you have to put your whole life on hold for 6 months to a year to rethink, retrain your mind, learn something new, and then take that information to teach your PhD students to do something else, right? So this is a great opportunity, and sort of the last opportunity this year, and throughout, you'll have the opportunity to take classes throughout, but for the most part, this year is the last big year where you're getting this nice formalized training. And after that, you know how all the books sort of condescendingly say, Introduction to Thermodynamics. Well, you'll be out of the introduction materials. You'll have to start doing the advanced stuff for everything. So, yes, so homework will be assigned. That's the moral of the story. All right, so recap where we're at. So to recap, I wanted to give a quick example with no numbers, of course, because that would make it too easy. Let's just say it's power generation. Because this is really the driving force of the Industrial Revolution, why people started caring about thermodynamics, particularly in the 17 and 1800s. We have a hot stream coming in and a cold stream coming out. So we have temperature 1, pressure 1 going out to temperature 2, pressure 2, and we have some work that we're trying to extract out of the process to run a steam engine, to run a loom, to run a lathe, to make machine equipment, to make textiles, whatever people wanted to make back in the day, whatever the hot item was in the 1820s. So the question though is, how do I maximize my work output of this particular process? Now what we can do is we can do our energy balance. And I hope that everyone can kind of come up with the energy balance right on the top of their heads. In this case, I've drawn as a negative, so I'll just put a negative here just to keep my nomenclature consistent. Now we're going to assume that this is well insulated. Any heat loss to the surroundings is of course going to be lost work. We'll make it a steady state process. And when we do a little bit of manipulation, let's see, so this is switch over to delta out minus N, W, yeah. That'll be our final energy balance. So our delta H, as a reminder, we're going to have our mass flow rate times by the enthalpy out. In this case, it's going to be at some temperature 2, pressure 2, and our enthalpy in, which is going to be, now that I switched my nomenclature, this is in minus out, so it's out minus in. Sorry, this does have to be negative here. And this is going to be at some temperature 1, pressure 1. Okay. So this is a classic type problem that you would solve maybe in a first week or two of a thermodynamics class, just like what we're working on right now. So the advancements in thermodynamics really tell us, well, the energy balance tells us how much work we can get out of the process. If we know what the enthalpy of the working fluid is at a particular temperature and pressure from the inlet and outlet streams, it's a really straightforward energy balance. Right? So once Carnot solidified the first law, then basically we had access to this here. Sorry, not Carnot, Joule. My classic thermodynamics is mixed up. Right? They took the second law for us to know that the path and the limits of what temperature 1 and pressure 1 and temperature 2 and pressure 2 should be were provided such that delta S should be equal to 0. The change in entropy of the process should be equal to 0. So if we look at our entropy balance, if we operate in steady state, we have no entropy change in the system. That doesn't mean there's any entropy generation, right? Steady state means that whatever the entropy is here, it's going to be constant. Right? Lasso my whole sort of power plant. Heat is going to be 0. We're trying to minimize heat losses, of course. Any heat loss to the surroundings is going to be lost work. And as we talked about in our last lecture, or maybe it was last week, I can't remember, if we generate any entropy, that also means that we're going to be running into problems with losing work. And that was the Helmholtz and Gibbs energy to find that. So what that tells us here is that the amount of entropy in has to be equal to the amount of entropy out, which draws the conclusion that the change in entropy going from inlet to outlet is going to be equal to 0. That's the most work that we could squeeze out of this process. Yes?
I have a question about the sign of the work.
This one here, yes.
Yeah, why did you add the minus by the equation below?
So in this, the reason why I drew the minus here is based on how I drew the diagram.
No, the one, the second equation.
So what I did to get from here to here, right? That's the question. So what I did is this summation. So this is going to be the mass times the enthalpy in minus the enthalpy out, because I'm just sort of doing bookkeeping. I'm just keeping track of all the streams in and out. Then I moved this term to the other side of the equation. So then it became out minus in, but the negative work remained on the right-hand side. So, with the combined first and second law, now we know how we can relate temperature 1 and pressure 1 to temperature 2 and pressure 2 such that we're not generating any entropy, which gives us the most efficient way to extract the most work out of the process. So let's say, for example, that we've figured this out for some temperature 1, pressure 1, some temperature 2, pressure 2. And that's for the boiler that you've already had installed that wasn't very efficient. But let's say you buy a new boiler from Michael's Boiler Company, and you buy a new turbine from Joe's Turbine Company. You have to say, oh no, I have to remeasure all of water properties all over again. Or let's say, for example, this process doesn't involve water. You're trying to do something a little bit more complicated, something that a chemical engineer would start to handle. Maybe it's an oil refinery, and you're trying to figure out how to manipulate the temperature and pressure of the oil, or expand it, recover work from a lost stream. Right? Maybe your process creates a byproduct that's a high pressure, high temperature fluid, and you want to expand it in order to generate a little extra power. Right? This is that process integration that chemical engineers are built upon. Now the question is, do you have to measure the enthalpy for every single fluid at every single temperature and pressure? No. It'd be so much easier if we could come up with equations for that. And thankfully, we did in the last class. So in the last class, what we did is we derived expressions for the change in internal energy as a function of temperature and specific volume. Now, the reason why we have changes in internal energy with respect to T and V is because it's actually the easier way to do it. So this expression is in your handout, the quote-unquote important table, which is very understated. And I can never remember these, so I always have to look them up. They're not necessarily what I would say the most intuitive equation in the world. These ones here, energy and entropy balances, oh, I can bust those ones out, no problem. These ones I struggle with always. We also developed an expression for enthalpy. In this case, it's very convenient because we've written it as a function of two easy to measure intensive properties, temperature and pressure, which is why we always, almost always want to work in enthalpy. Because it's so much easier and it relates to open systems. And lastly, we have expressions for enthalpy as well. Sorry, entropy, did I say entropy? Enthalpy. And this one here is a function of temperature and pressure. And lastly, we have an enthalpy expression as a function of temperature and specific volume. Again, in my mind, specific volume always sounds a little bit tedious. I just instantly think this is density, the reciprocal of density. But mathematically, that's confusing as I can understand. Now, the counterintuitive thing always is that it's actually easier almost to calculate entropy changes than it is internal energy and enthalpy and any other properties. The expressions for entropy are almost always the pretty compact, elegant ones. So what this is telling us now is that, as a reminder of how we got here, this is the combined first and second law of thermodynamics. Really all we did is we substituted Q from the entropy balance into the energy balance, and then we generalized it for basically all systems. So we don't have to make any assumptions about the system. So these equations are only restatements of these two expressions, but just written in a slightly different differential form. Then we took advantage of the fact that every thermodynamic property for every single component, single phase fluid can be described by two variables. In this case, we have internal energy as a function of temperature and specific volume, enthalpy as a function of temperature and pressure, and same on for the entropy expressions. So, if you need to, do this yourself. Go back through and just reproduce what I did in class last time and convince yourself that these are not just made up expressions. They are only a consequence of the first and second law and general multivariable calculus constraints. And this is why they say, you don't really understand thermodynamics until you teach it. But go back and convince yourselves that these are the expressions and how we got them. In the course of 50 minutes, we derived everything. So that's all these are saying. So these are general statements that are always true. We've made no assumptions whatsoever. The only thing that we've done that's any sort of trickery here is that we have defined C sub V as the change in internal energy with respect to temperature at constant volume, and C sub P is defined as the change in enthalpy as a function of temperature at constant pressure. The reason for that is we don't know how to calculate it, right? Classical thermodynamics didn't even know that molecules existed. So we didn't necessarily have a good governing overarching theory as to why some materials heated up very easily and some materials did not heat up very easily. Now we know that something like methane heats up very trivially because methane only has a very small number of ways to store energy. So if I give a joule's worth of energy to a mole's worth of methane, it really can only rotate a little bit faster and translate in X, Y, and Z space a little faster. Yeah, there's a little bit of bond vibrations, but actually bond vibrations are harder to activate than you may think. Now, this is in contrast to something like decane. Decane is a big molecule that has lots of mass. So if you want to give it more kinetic energy, it takes a little bit more push to get it moving. So its heat capacity is going to be higher. It's got many more vibrational and rotational nodes. It has more complicated vibrational nodes, right? So if you have a carbon-carbon system like this, it can actually flex and bend this way, it can vibrate this way, and it can rotate among each of these axes as well. So that's why decane has so much higher of a heat capacity. But classical thermodynamics, remember, we didn't even know what the atom looked like. We were still in the plum pudding model. We didn't know what an electron was. We didn't know what a nucleus was. So for these properties, we just had to rely on the fact that these were some things that we had to measure. So now the additional complication is, in order to even use these expressions here, we need to have access to accurate information of the heat capacity of every fluid as a function of the state of the system. So we may ask ourselves, well, what is the point of all this then? If we have to measure the heat capacity of a fluid as a function of its density and temperature, or the C sub P as a function of its temperature and pressure, why should I bother tabulating this information? Why shouldn't I just measure the enthalpy and internal energy and just make a big table? Why do I even care about the heat capacity?
You don't have a gauge to measure those things.
Well, that's true. We don't have a gauge to measure the heat capacity either necessarily. We'll infer what the heat capacity is based on how much, basically the slope of the, let's see, put it this way here another way. If we look at enthalpy as a function of temperature, it will look like this almost always. The heat capacity is going to be the local gradient there. So if we have the enthalpy, we can calculate the heat capacity. But the answer is, we can be clever about it. We don't actually have to measure the heat capacity at every single state of the system. We can calculate it using an equation of state. And I'm only showing this as an example because it'll highlight why we don't actually even use this at all. We can be even more clever. So step one is a slightly clever solution, and then step two is a much more clever solution to this problem. So what we would need then is if we can integrate from some state one to some state two, how the heat capacity is changing with respect to the density of the fluid, then that will give us a function, let's see, T and V. So if we were to measure the heat capacity only as a function of temperature, in this case, I'll give you a little preview, we'll measure this for an ideal gas. right? If we can only measure the heat capacity of a fluid as an ideal gas, then if we have an expression for how the heat capacity changes as a function of its density, we can then derive an expression for how the heat capacity is going to be at any particular state of the system. So that reduces having to measure the heat capacity. So let's go back. We need access to the internal energy and enthalpy as a function of every temperature and pressure configuration. All right. We write out these expressions, but all these expressions have done is now said, okay, now all we need is the heat capacity at every single temperature and pressure. I said, okay, let's simplify it a little bit more. Now we only need the heat capacity at the ideal gas state and an equation of state that relates between temperature, pressure, and volume, and then we can calculate everything we need to calculate. Like I said, we're learning this system of thermodynamics. This is the best system that people have come up with to accomplish this task. So, as an example, we'll go through and actually calculate this with V. So if we expand the internal energy with respect to temperature and volume, right? This is exactly what we did to start off our derivations earlier in the week. We're going to directly relate this to our expression right here. So this is the definition, for this case here, of heat capacity. And then this one, I'll just rewrite it. Okay. And again, we'll use a little bit of clever mathematical trickery. And what we'll do is we'll switch the order that we take the derivatives of each of these ones. So because all thermal functions are well behaved, so if we take the derivative with respect to volume at constant temperature of, this is equal to dV at constant T. This side of the equation we don't really care about, but this side of the equation here would basically be this expression, taken the derivative to dt. This expression here, we take the derivative dv. As it turns out, this is exactly what we're looking for. Any questions on this? Got a little quick.
So you took the second differential of du?
What I did is I used these two terms, right? This is the definition of the heat capacity, C sub V, which is the change in internal energy with respect to temperature. I wanted to get access to the change in heat capacity with respect to specific volume. And I just so happen to have an expression here for how the internal energy changes with respect to changes in volume. So by using a little bit of thermodynamic mathematic trickery, I noticed that these two expressions are exactly the same. So taking the volume derivative of the temperature derivative is the same thing as taking the temperature derivative of the volume derivative. This term just happens to be exactly what we're looking for. And we have a nice convenient expression for how internal energy changes with respect to volume. So let's go over the calculus really quickly here. If I take the derivative with respect to temperature, I have to use the product rule for this first term. So dt dt is equal to 1 times by this, so dp dt at constant volume, and then switch. So then I have plus temperature times So far, so good. This cancels over here, and that the change in heat capacity with respect to changes in the fluid density at constant temperature so the equation of state contains all of the information to know how the fluid is going to change. And I'll highlight that in just a second, but let me write down a similar expression. We can go through identical derivation just by starting off at a different point. We can look at how C sub P changes as a function of pressure. I'm not going to show the derivation, but it's a very similar approach. All right, so here are two expressions. Now, I don't want to move on before going over the equations of state a little bit. Okay, let's go through a quick example of some equations of state. All right, what's our famous, nice, convenient starting point for equations of state? We love the ideal gas law. All right, what's a slightly more complicated? What is the one, well, there's another one that's in between that we commonly use called the virial equation of state. But let's go one step further and let's talk about the van der Waals equation of state. This is the van der Waals equation of state, which won him a Nobel Prize, and this was his PhD thesis. So, I'm not anticipating the Nobel Prize Committee is going to be calling me on my thesis. So very quickly, for an ideal gas, do we expect the heat capacity to be a function of the pressure or density? Just intuitively and then mathematically. So intuitively, should the heat capacity of an ideal gas depend on how close together the molecules are? No, because in an ideal gas, they must be infinitely far apart. Now, infinite doesn't mean on opposite ends of the universe. They have to be far enough apart that they have no influence on each other whatsoever. That is the assumption of the ideal gas law. And we can also see here that if you take the second derivative, right, with respect to pressure, this is not going to be around. Same thing here. Right? So even the mathematics of thermodynamics demonstrates that. However, when we have a more complicated equation of state, and unfortunately I didn't work out the math of what this function is for the van der Waals equation, but we can see that there's a possibility that the van der Waals equation of state, or the Peng-Robinson, or the virial equation of state, they will have some nonlinear, more complex functional relationship with some of these more with these thermodynamic properties to be more realistic. Makes sense. So that all being said, this is really not at all what we want to do. This is still far more complicated than how we typically will do thermodynamic calculations, because there's better ways to do it. So if we wanted to get access to, just hypothetically, let's say we wanted the heat capacity at some pressure and temperature value. What we can do is we just need to integrate this expression here. So if we integrate this is what we would have to accomplish. What we'll do here is we'll say that the pressure 1 is equal to 0, which means that this is the ideal gas state. And so we will write this, that the heat capacity at pressure equals 0 at some temperature. We will write this in our notation moving forward as the heat capacity star, and that it's only going to be a function of temperature. So if we do want access to the heat capacity of a fluid at a particular temperature and pressure, we still need to have access to the heat capacity of the ideal gas state. We add that to the contribution here from an equation of state. Now that equation of state, we should expect, must have this term here in order for there to be a change in the heat capacity. So this is a little bit ahead of what we're trying to accomplish here, but in the van der Waals equation of state, R, T, V, we know what those ones are. What does the B term represent?
Volume of the molecules.
The actual volume of the particles themselves. So this is the free volume. So V minus the excluded volume tells us how much the molecules can actually move around. What does the A term represent? The intermolecular forces. So if we don't have any intermolecular forces, as we squeeze the molecules closer and closer and closer together, we shouldn't expect their properties to change. But if they're attractive or repulsive, then as we squeeze them together, we should anticipate that their heat capacity should be changing a little bit. So that's why we need a more complicated equation of state that accounts for the real physics of the process to understand how particles are going to be changing in a real system or a real fluid. So as a default in this class, I know that maybe in an undergraduate thermodynamics class, it is nice to just assume the ideal gas law to work through problems, but the whole point of this class and more advanced thermal classes is to not assume ideal gas. So in this case, we're almost never going to use ideal gas relationships. I'm going to keep these expressions up on the board here. All right. So, let me see. I want to squeeze this in. Now let's get to the actual practical objectives here. Let's do pressure and temperature. Now, going back to the start of the class, what our objective was to modify our process such that we could take any arbitrary fluid at any initial condition and find out what is the maximum way to get to some final condition such that we have the most efficient process where we're extracting the most work out of our turbine, or our turbine boiler, or our energy recovery unit that's going to expand some process fluid to get a little bit more energy out of it. So what that means is that we have two states. In this case here, I actually write the opposite. I'll say this is temperature 1, temperature 2. So we're actually going from low pressure to high pressure. Pressure 1 to pressure 2. We have some process where our fluid is entering here and it's leaving there. Now how we go from process 1, from state 1 to state 2 is going to determine how much work we're getting out of the system. That actually turns out to be related to the entropy. However, for delta S and delta H, we only need to worry about the end positions to find out those final endpoints. But how we would actually design the blades or how we would expand it, that all becomes a little bit more complicated. But in terms of what my starting point and end point are, I only need those two positions. So the key question is, let's say hypothetically I wanted to, in the real process, maybe it goes something like this, right? Maybe it goes like this. Maybe it goes straight line across. But all of these scenarios have problems with respect to how we do the math. If I am going on a diagonal line over here between temperature 1 and pressure 1 to temperature 2 and pressure 2, that means I'm changing both variables at the same time. So if I want to integrate any of these expressions here, everything in the equation is changing at the same time, and we don't have a way to solve that trivially. So instead, we only want to walk in straight paths. Now, intuitively, we may think, what is the easiest way to go from here to here in straight lines? And we're going to throw out a guess. So we go over, and then we go up. Right? That seems like the easiest way. We can conversely also go up and then over. Right? Those are both acceptable ways. In my notes, I have this as path 2A and path 2B. Actually, put this in a second. Now, why do I have them as 2? What do we think is actually maybe the easier way to accomplish this? There's one easier way to do this. It seems harder, but it's actually easier.
Changes the ideal gas from ideal gas state to ideal gas state.
Exactly. 1A, 1B, 1C. So let's talk about this for a second. Now, I told you that this is a method that we can use. But I personally don't enjoy taking the second derivative of a complex function and then reintegrating it. And then reintegrating it, not just numerically, but analytically, so that I can determine what the heat capacity is at every single point along all of these lines. I personally don't want to do that. So in order for us to take path 2A, that means we need to know not only how does the heat capacity change as a function of temperature, but how that also influences that at every single pressure along the way. Because in a real equation of state, and I wish I had an infinitely sized chalkboard over here, right? But if let's say we take even the simplest equation of state that predicts the existence of a liquid, in general, sometimes this A term for simple equations of state is not going to be a function of temperature. In more advanced ones, it may be a function of temperature. So in a simple equation of state, maybe you only have to do this integration once, and you have an expression for how the heat capacity is as a function of pressure. Maybe for a fluid that's very commonly used, that's the best way to go. But that effectively means that you have a double integral in your expression, right? Not only do you have to do this integral here with respect to pressure, but then when you're trying to solve this part of the expression, you have to then integrate it with respect to temperature. I don't like doing double integrals. I'm not very good at math. So instead, what we'll do is we're going to go down to the ideal gas state. We're going to heat it up as an ideal gas, and then we're going to repressurize it. And so what that'll actually look like mathematically, I'll write it out the steps as follows. So, starting off, step 1A, we're going from pressure 1 to pressure 0 at a constant temperature. So if we look at this expression here, right, this is the one that we're working with. What goes away in step 1A? We're going from pressure 1 to pressure 0 at a constant temperature. So if temperature is constant, what is 0 in this expression? dT. Right? There is no change in temperature, so we don't actually have to worry about the heat capacity whatsoever. We only have to integrate this expression here. So in this case, we would be integrating dH, the change in enthalpy, from pressure 1 at constant temperature to pressure 0 at the same constant temperature. This is going to be equal to the enthalpy at 0 pressure temperature minus the enthalpy of the initial state, pressure 1 temperature, which is going to be equal to integrating this expression at CV minus 2. Again, right, for an ideal gas, this goes to 0 because minus V is exactly equal to this expression here. For a real fluid, it's not equal to 0. Next step, we will do 1B. In this case, we're going to integrate from pressure 0, temperature 1 to pressure 0, temperature 2 of the change in enthalpy, which goes to 0 in our change in enthalpy expression. dP goes to 0. Thank God. You don't have to worry about this big expression. There's an additional simplification. All we have to do here, let me just write this out again. So this is enthalpy of 0 T2 minus enthalpy of 0 T1. This one's nice and convenient. Thank goodness. Right, this is something we're hopefully very used to. Right? This should be a very common expression when we integrate heat capacity. So when you go to the back of a thermo textbook, how do they organize heat capacity data as a function of temperature? Anyone remember?
1 plus D squared.
Right, it's some polynomial expression, right? So it's typically written like this. C sub P is equal to A plus B T plus C T squared plus D T cubed. Sometimes it's 1 over, sometimes it's a logarithm thrown in. Anyone want to venture a guess as to why they provide heat capacity as a function of temperature in this functional form?
Easier to integrate.
It's very easy to integrate. Super easy to integrate. But as it turns out, this is a really bad functional form for thermodynamics. Because what happens, and hopefully any of your undergraduate research advisors or in your classes as an undergraduate, someone's pointed this out to you. If you go to Excel and you're trying to fit your data, you say, oh, linear doesn't fit. Let me try a second order polynomial. Well, let me try a third order polynomial. I'll try a fourth order polynomial. And you'll get something that looks like this. Right, so let's say this is heat capacity. Let's say this is temperature. Polynomial functions do this all the time, where they reach a maximum, a minimum, an inflection point. That's very, very bad in thermodynamics. Inflection points and maximum and minima means that you potentially are violating the second law of thermodynamics. So as it turns out, this functional form here is terrible when it comes to the science of thermo, but it's very convenient when it comes to actually practically solving real problems. So there's better functional fits here, but for students, this is super convenient because you can integrate a polynomial in the blink of an eye. I don't think anyone who's taken calculus will ever forget how to integrate or differentiate a polynomial. So that's why it's organized this way. All right, that's a nice aside. So anytime you do end up using a polynomial fit, every time you see a minimum or inflection change, ask yourself, is that a real physical phenomena of the process or is that just a consequence of the fitting? I promise you it'll come up in your research. Lastly, step 1C is just going to be the same thing that we wrote up here, but we're just going to change the limits. In this case, we're going to go from 0 at temperature 2 to pressure 2, temperature 2. Let's be thorough here. Let's see, I don't know if this is P2, T2, 0, T2, which is the integration. All right. And all we do is we just add up all of these contributions and we have magically determined what the delta H is for all of this. So if I add up 1A plus 1B plus 1C, this will be equal to my total delta H which is the enthalpy at state pressure 2, temperature 2, minus the enthalpy at state pressure 1, temperature 1. And that is exactly what I'm looking for in my energy balance, as the example that we started off with power generation. Because we'll see that we have a plus enthalpy, a minus enthalpy, a plus enthalpy, a minus enthalpy. And the only terms that we are left with are the initial and final states of the system. And this is how we calculate and build steam tables, but instead of actually going into the lab and measuring it, all we actually have to measure for this entire process to hold true is the heat capacity of the ideal gas of the fluid and how it changes as a function of temperature. And we need an equation of state that accurately describes pressure, temperature, and density relationship. So with many regards, we only need two things. What is the density of the fluid as a function of temperature and pressure? And what is the heat capacity of the ideal gas as a function of temperature? And those are the only two things that we ever need to measure for us to calculate all fluid properties of mixtures, of phase changes, entropy changes, any fluid going through any real process. So where we started was having to measure this at every set of conditions. So for steam, it makes total sense. We use steam a lot. But for being creative and designing new chemical processes, it's not necessarily going to be the most effective way. Any questions? So we'll do one more quick example, but in this case with entropy. Entropy does have a little bit of tricks, because you have discontinuities when you're dealing with entropy. So let's look at doing the same path, in this case, but for entropy. So we're going to be using this expression right here. I'll just rewrite it for the notes. Okay. So we want to go the same paths. So we're going to go 1A, 1B, 1C. I won't go quite through the same level of detail. So in the first step, we're doing an isothermal. So our 1A contribution is only going to be, so let's see, integral here from P1 T1 to 0 T1. Our next contribution is just 0 T1 0 T2. And our final contribution put it all together. You know, I'll leave it at that. I'm just rewriting the same thing. I'll just say 1A plus 1B plus 1C. There's one problem though with this approach. What is the entropy of a fluid with a zero density or at zero pressure? It is infinite. So the problem with entropy is that I cannot calculate this part and this part independently. So what we're going to be doing when we talk about entropy changes is we're going to be giving it effectively an infinite amount of entropy, and then we're going to be taking away an infinite amount of entropy. But the convenient thing is that we can combine these two integrals here, and that we don't have to actually get a quantitative answer for each of them along the way. Another nice little trick when it comes to entropy in ideal gas states is that when you're going from your real state, let's say state 1, to let's say state 2 being an ideal gas state, you could kind of be a little bit sloppy and cheat and basically say, if you know what the properties of the ideal gas state are, you can kind of slide those ones in. So a lot of times when I do integrations in the future in the class, I'm not going to write out T1, P1, T2, P2. I'm instead going to write out state 1 to state 2. It's sort of a quick hand notation knowing that, yeah, I am changing this here, but I can also, in some of my derivations, I can say, yeah, state 1's a real fluid, state 2 is an ideal fluid. I know that an ideal fluid has X property in whatever state. So then I can kind of take two theories approaches and put them together. And that's something that we'll do sometimes. But for the most part, just being a little bit rigorous with respect to entropy here, because you can run into values of infinite entropy when you go to an ideal gas state. Okay, so I will send out the homework sometime in the near future, but I promise I will give enough time. If I don't give enough time, please let me know. Like I said, homework, I intend to be there as a learning tool, not a test or a quiz. We already have tests and quizzes that can be used as learning tools. All right. Football game is tomorrow, so don't have too much fun. And see you all on Friday.